Good morning, everyone. My name is Scott Friedman. I'm the team manager for Team 4, Brandon's detented joystick. My teammates, Nathan Hyde, who is our lab coordinator, Addie Matthew, who is our document prep, Peter Ossian, who is our webmaster, and Young Jayu, who is our presentation prep. Our facilitator this semester is Dr. McGuff, and like Team 3's, our project liaison is Mr. Stephen Blosser from the RCPD here at MSU. I will hand it over to Nate, who will go over our agenda.
All right, thanks, Scott. And so once again, my name's Nate, and I wanted to start things off by giving everyone a rundown of our agenda today. So we're going to start with an introduction, give everyone some background information about cerebral palsy, kind of some insight into Brandon's situation. Next, we want to get into the current joystick design, which is seen right here. This is kind of the design we're going to be building off for our project. Next, we're going to get into the design specifications that we've come up with, things we need to improve upon with this model, and we've come up with these with the help of our sponsor. Next, our ideal design solution, what we need to do to make the improvements to this to make Brandon's life easier. And finally, we're going to touch on some project management aspects, things such as time and money, how we're going to make this happen. And then we'll wrap it up with a summary and then open things up for some questions. All right, so first off, what is cerebral palsy? It's actually a broad term, and it's used to describe a number of disorders that affect brain and nervous system function. Some classic cerebral palsy symptoms, you have abnormal muscle contractions, loss of coordination, partial paralysis, and even loss of speech. So kind of the key thing to note with cerebral palsy is that in most cases they have the same mental capacity as you or I, and it's basically their ability to communicate with others where they struggle. They don't have like the fine motor skills to really communicate with someone else. And so every year in the United States there's 10,000 people diagnosed with cerebral palsy, and that's kind of at the infant stage. And then kind of by the age of preschool there's going to be another like 1,500 or so that are diagnosed. So this is something that affects a lot of people. In Brandon's case, he's got what's called apatoid cerebral palsy. And as you can see in the picture here, he's restricted to a wheelchair and he doesn't have the ability to speak. And so he has to rely on a type of assisted technology, which is the detented joystick. He's actually had some troubles using this because of the lack of fine tuning. And so that's why we have to make it our goal to improve upon this to make things easier for him. Throughout our design process, we're going to be working closely with Mr. Blosser, and since he's got experience working directly with Brandon and he's the designer of this joystick, he's going to kind of give us what we need so we can make a product that directly caters to Brandon, but then also is flexible enough to work with other people with cerebral palsy. So kind of with that, I'm going to turn it over to Addie, and he can give you guys an idea of exactly how this joystick here works.
All right. Hello, everyone. My name's Addie, and I'll be explaining how the current model of the joystick that Brandon uses, and even faculty at MSU, by the way, use today on a daily basis. Well, why do we need to do that? The first reason why we need to do that is to improve on a design of something that's used every day. We need to understand and fully appreciate why every component works the way it does. So let's begin by taking a look at joysticks. How do they work, and why does a person like Brandon need them? Essentially, they are a human interface device. You push a button, you move a stick, you move something bigger, you move something that you would not otherwise be able to move, be it a video game character, a mechanical linkage, or even an aircraft. So how does this benefit Brandon? Well, essentially you can see it's a tool. It's the same for Brandon, but not the same way as it is for us. How? That's where detenting comes in. What is detenting, and why does Brandon need it? Detenting is pretty simply put a force in an opposing direction of motion. And for the joystick, for us, it's the center, recentering to the center of a joystick. For Brandon, it's detents, incremental spasms of force opposing his pushing on the joystick. The closest thing to imagine this is, imagine two people arm wrestling. You have locked palms and pushing in opposite directions. Now imagine one is the detenter, whatever that is, and the other is Brandon's hand. Pushing each other. Now suddenly Mr. Detenter here starts giving spasms in the opposite direction, letting Brandon push in the same direction he wants to. Speed that up 10 times and you get detenting. Why does he need to do that? As Nate said, people with CP, they lose muscular coordination. They find it hard, if they want to do something, they're either going to spasm their way toward it or overcompensate and give it a hard shove. The closest thing any of us can possibly do to experience that is intoxication, getting drunk, and it's magnitudinally less so. So, how is detenting achieved in the current model? That's what we see here in the current animation. You have a cog wheel, 10 teeth over here that rub on this rubber stopper. Now this rubber stopper and these teeth are purely mechanical. There's no electrical components in these moving pieces. So the first drawback you can see to this design is mechanical wear and tear of these two parts. When they wear out, someone, definitely not Brandon, is going to have to screw these two out and remove this tooth. Now, that's a major drawback. He cannot move the joystick. He finds it difficult to move a joystick, let alone replace this part. That's one of the goals we aim to improve upon. Now, how is this mechanical motion translated into digital languages? That's where the position sensing of the same joystick comes into play. You have the teeth, you have 4 IR sensors and 4 IR emitters at the bottom here. These play off of the reverse side of the tooth. You can see a pattern here. This is a rotary encoder implementing 4-bit gray code. Essentially, this gives you possibly 16 teeth, 2 raised to 4 16, and each position, each one of these teeth is a detent. So you have individually identifiable positions on each axis, 16 of them as a max for this hardware. If Brandon needs to swap these out, he's going to need to swap out this entire part. If he needs more than 16 detents, this entire thing needs to be replaced. So, how is this position translated into a computer language, or transferred to a computer, I should say? That's done by an 11-pin parallel port. As you can see, Brandon's technology is terribly out of date. Even his computer, the program he uses, runs something called Vocaman. It's a voice synthesizer, and he uses the joystick to select words on screen. Each detent is one word on the screen. He selects the word, outputs it, the synthesizer speaks it for him. It runs MS-DOS. That's how old it is. How do we improve on this? That's where I'll leave it to Yung Zhao to explain to you.
Hi everyone, my name is Yung Zhao. I will introduce 3 main design specifications we have for our new design. The first one is adjustable number of detents and adjustable detent force. The reason why we need it is because the first reason is just simple. Users just can't adjust the settings. They have to ask other people for help and use a screwdriver to adjust the. Use a screwdriver and remove the mechanical parts inside of the joystick in order to adjust the detents. The second reason is there's wide range of users with different needs. Like Nate have introduced in the introduction part. There's a wide range of users with different detent needs due to what kind of CP they have and how severe it is. CP usually appears in large range of symptoms. Some are paralyzed, and some people have weak control over their own motions. All the different types of CP and severity the patient has leads to different detent needs of the customer. Those with more severe symptoms usually need more detent force and less number of detents. Unfortunately, within the whole population who suffer from CP, only a limited portion is physically capable of using the joystick as an assistive tool. So as far as we can do, we want to enlarge a portion as large as we can so that we can we can make more people benefit from our design. And another reason we want to do detent adjustable design is because of the changing symptoms for the CP. Even for the portion of people who could use our joysticks, they will have difficult time trying to use it due to the unstable nature of CP itself. Patients' symptoms sometimes get better, while in other days it gets worse. That's when they will have to change their needs for the number of detents and detent force. Therefore, with the detent adjustable joystick, the range of the customer will be increased in large scale, and the new product will be much more user-friendly. The third goal that we have here is USB output and connectivity. With the USB connection, users will have more computer flexibility than before. It doesn't matter anymore if they are using a laptop or a PC, a desktop PC. The joystick system will always the joystick system will always recognize what kind of input design it is and recognize the whole system. The next reason why we need USB output is because the first two specifications here is all accomplished by the third specifications, which is USB output and connectivity. Through USB interface will make it programmable, and then that's achieve the first two goals. And another reason we need USB output is because of the power supply. It's a power supply for our microcontroller. And while we will implement all these three specifications, I will pass it on to Pete who will explain how to do that in hardware and software aspects.
Thank you, Michelle. Hi, my name is Pete, and I will be covering the software and hardware portions of our design. We have gone with two actuators here, which will account for position sensing, and they will be vertically aligned, as you can see in the diagram. One will correspond for the X direction, and one will for the Y. And basically, we have load sensors attached that will register a spike of input, which will be when the user pushes firmly in one direction to confirm navigation. And from that spike, we will then control the actuators and give signal. Pretty much, we have our positioning and sensing stuff goes through our software. And leading to our software, we basically have a microcontroller, which will serve a couple features here. It will have adequate number of inputs, USB functionality, low cost, ease of programming, and it will have a small package size. So from this, we will basically implement a software which we have two data paths. One pretty much for the in-user navigation once the joystick is moved and data is sent from the actuators and received in from the microprocessor, and the output will be sent to the software and control the matrix lets Brandon or the user select which word he's going for, and the other one will calculate our force feedback and pretty much send that to the software and work with the joystick. Pretty much we chose this setup because the force, the actuators will move based on the number of detents and direct the force. So basically for this data path, as I was describing, when feedback is sent, the actuators will be able to adjust by going in reverse, therefore creating a feedback. So the user will know he has to apply a certain amount of force to get past each detent to move into the next one for navigation. And the load sensors naturally we chose because they would give us that point where input would be registered as the seen on that graph before. And this setup will allow us to control the number of detents that we need. These are the components and design strategies necessary to meet our specifications, and now I'll pass it to Scott to discuss project development process by our success.
Thanks, Pete. So one of our biggest assets in our group is our personnel. The way that we've designed our team, we're going to have an electromechanical design that I'll help lead. We'll have a packaging lead, which will be Nate, and then testing will be done with Young Joe with all of our help, and then also the software design and software tests and support will be done by Addie and Peter. With that, we have our development in 4 phases. Phase 1 will be research state-of-the-art, which you can see we've extensively done by researching the existing joystick that is actually still being used today and on campus. We've done a lot of work in seeing the faults and kind of the successes of the current design. Phase 2 will be a concept creation where Pete kind of went through the 2 actuator design with the built-in load sensors and position sensing. We believe that that's probably the best route to go, and so does Mr. Blasser as well. Phase 3, which will be prototype development, and there we'll actually order our parts, design our product and our final packaging, and see. Then that will lead us into phase 4, which will be our testing, where we're going to be able to interface with Brandon and see that our joystick is what he needs and give him the outputs that he wants. We can go here. So another part of project management is the budget justification. Our budget is kind of simple, where we only have 3 main areas that we're going to split up our money. Electromechanical components will be our biggest cost. The 2 actuators, load sensors, any other linkage that we want as far as electromechanical components are concerned. We budgeted about $300 for the total cost of that. Our microcontroller board will be a little bit less expensive because we'll be going either with an Arduino or maybe a Teensy board. It's a low-cost board, but it'll still give us all the necessary inputs and outputs that we need. We budgeted about $75 and then left a contingency budget of $125 for shipping and other miscellaneous costs. A couple interesting things about our budget, though, is that the mechanical linkage developed by Mr. Blasser will be reused, and any adjustments that we need to make will be developed in-house. So that will eliminate some of that from our budget. Also, Brandon uses a motorized wheelchair that we have access to the power supply on board, so we won't have to actually pay for a exterior power supply to power our joystick or the actuators in. And then also our housing and packaging, which in the old model we do have packaging, but with the actuator design it might need to be enlarged, or we might want to change the packaging and how it's mounted to his wheelchair. And so that way we're also going to do that in-house, either by the ECU shop or Mr. Blosser also has a machine shop in his. So with that, I will leave it to Nate, who will go over some.
Alright, so kind of to wrap things up, we started things off today taking a look at cerebral palsy and Brandon's situation right now. That took us into looking at the current joystick model. This is where we found what needs to be improved to make Brandon's life easier. And so kind of with this model and then the help of our sponsor, we came up with our design specifications. The 3 main goals we need to accomplish: we need a programmable number of detents, a programmable detent force, and then USB connectivity. Our design solution, we're going with 2 actuators, one to control the x-axis, one to control the y. And these are going to be used in conjunction with 2 load sensors, one for each axis. And the microcontroller is serving as our kind of means of communication, so that when a load sensor picks up a threshold force that we've determined, it can tell the actuator to move to the next position. And so to wrap things up, we took a look at our timeline and our budget. Right now we're kind of in between our concept creation and our prototype build. The prototype we'll kind of get things rolling with that in the next coming days and weeks. And then as far as our budget, the main portion of it is going to be going towards our electromechanical components such as the actuators and the load sensors. We also have a good chunk going towards the microcontroller. And it does leave us with some flex room for any unseen costs and also shipping. So with that, I think we'll open it up for any questions anyone has.
Question from the class? I just had one quick question. Aren't there other companies making these things, or
Not to the extent that we need.
nobody?
Not a lot of
All right.
force feedback joysticks currently on the market. Actually, return to center. They don't keep position, and also they don't give enough force feedback to eliminate physical noise that would be like a tremor from a CP-patient.
Okay, so it has to have that resistance.
So it has to have that resistance and also that guided motion.
Okay, all right, good job. Thank you. Before you go, one quick thing, one quick